Hello everyone. This session is the continuation of the previous session. So here we are going to talk about gradient, divergence and curl, and also directional derivatives. So directional derivatives is a part of gradient. So let's start. Till now we have seen that any vector 2i plus 3j plus 4k has three components. All these components are constant. That means 2 is a constant, 3 is a constant, 4 is also a constant. So 2, 3, 4 is the point, that is the vector. But now we are going to extend our idea. That is, instead of constant components, we may have components as function. So let's say we have a vector f that is equal to 2x y I plus x squared y j plus yz k. So this time we have the components 2xy, x squared y, yz. That means if we collect the components 2xy, comma x squared y, comma yz, just like 2, 3, 4, this is the vector. So similarly, here we have f equals 2xy, comma x squared y, comma yz. So this time the components are functions. So f is a function where x comma y comma z are the inputs. That is, here we have x, y, z. So we have three input variables. That means this is dealing with function of several variables. We have learned what is function of several variable. If the number of input variable is more than one, then that function is called the function of several variable. So here f is a vector which is a function of three variables. So this vector is a combination of three functions. Let's say 2xy, x squared y, and yz. So these three vectors are also function of x, y, z. We can write by this way: p of x comma y comma z comma x squared y, here q of x comma y comma z, and the last one yz will be a function of r of x comma y comma z. So this function f is a vector function where p, q, and r are the components which are also functions. So we can easily understand the difference between this vector and this vector. So here f is a vector where the components are constant, but here we have the components as function. So this is the example of function of three input variables. We can think about function of two variables. Let's say we have a vector f equals x squared y I plus y squared minus x squared j. So we have I and j. That means this function is two-dimensional vector. So here x squared y, we can write this one as p of x comma y. This time we have two inputs x and y, I plus y squared minus x squared can be written as q of x comma y with j. So since p and q are functions of two variables x and y, so similarly the vector f will be a function of two input variables x and y. So that means in short we can say f equals pi plus qj. So a function can be of two variables or three variables. So this time we have seen that these components x squared y and y squared minus x squared are functions. So if we have a vector with the components as functions, then that vector is called the vector field. So we have seen some figures earlier that here we have seen that there are vectors in different directions. These are the vectors. Here we can see that this is a vector, this is another vector, this is another vector. So collection of all vectors is a vector field. From this function we can generate many vectors if we input the values of x and y. Let's say we have a vector field of three variables x comma y comma z, that is equal to x squared I plus yj plus z plus 1k. So this is a vector field of three variables. There are three inputs. So this is a vector field because the components are functions. Let's say this is p, this is q, and this is r. All these p, q, and r are functions of x, y, and z. So we can generate many vectors from this vector field. Let's say we are going to input x as 1, y as 1, and z as 1. So if we input the values here, x squared, 1 squared, I plus yj, the value of y is 1, so 1j plus z, z is 1 plus 1 k. So we have 1 squared I, that means 1i or I, 1j, that means j, 1 plus 1, that is 2k. So from this vector field we can generate a vector where we have the constant components. That means from vector field we can generate many vectors. So this vector can be directed by an arrow. Similarly, if we input 0, 0, 0, that is x is 0, y is 0, z is 0. So x squared, 0 squared, that is 0, plus y, that is 0. So 0j, that means 0, plus z, z is 0, and we have plus 1. So we are giving input 0, 0, 0, and we are getting the output 1k, that is just k. So that means From this vector field, we have generated another vector at 0, 0, 0. So that means vector field is a collection of vectors where the vectors have constant components, but the vector field is a vector function where the components are functions. So in a word, we can say that vector field are the collection of vectors. So vector field is also known as force field, since the concept of force is coming. So that's why we denote vector field as F. So the letter F is used as vector field or force field. So now we have to discuss about gradient, divergence, and curl. So gradient is denoted by grad f or del f. Divergence is denoted by divergence of vector field f. Curl is denoted by curl of vector field f. So we can see the difference. In grad, the function that I have written here is not with an arrow sign. That means this function is scalar function. So what is the action of gradient? Gradient converts a scalar function to vector. That means gradient converts this function to vector. Divergence. In divergence, we have a vector field. So divergence will convert a vector to a scalar. Divergence is also acting as dot product. Curl. Curl of f. So here we have f vector. By using curl, we'll get again a vector. So from vector to vector. So curl can be similar to cross product. We have learned what is cross product and dot product. We have another term that is known as directional derivative. So directional derivative is denoted by du dot f. So since dot product is coming, so it will be again a scalar. That means by gradient we will convert a scalar to vector, and by directional derivative that vector will be converted to again a scalar. The meaning of divergence is the tendency to diverge from a point. Divergence is also applicable to understand whether a fluid is compressible or incompressible. By curl, we understand the circulation or rotation, that is, the tendency to rotate around a point. So if divergence is 0, then the fluid will be incompressible. If divergence has a value that is non-zero, so we can say the fluid is compressible. By curl, we understand the rotation. If the curl of F is 0, then there will be no rotation. So it is called irrotational or conservative field. If curl is non-zero, then we can understand that there will be rotation because curl has a value, so it will be rotational field. So if curl is 0, then the field F will be irrotational or conservative. If curl is not 0, then it will be rotational field. So if divergence is 0, it will be incompressible. And if divergence is not 0, then the fluid flow will be compressible. So let's talk about all this part. First, let us talk about the gradient of any scalar function f. That f can be a function of 2 variable or a function of 3 variable. So these functions are scalar functions because there is no vector here. So these functions can be f of x comma y equals x squared y negative y cube, f of x comma y comma z equals x squared plus y squared plus z squared. So these are the examples of these scalar functions. So the gradient that is denoted by del f, we also know this one as grad f. So gradient of this function f will be del f, and by del we know that it is ddx I plus ddy j if it is two-dimensional function and f. So we are just plugging the vector for this del. So what we can do, we can multiply f with ddx, so we are getting df dx I plus df dy j. So we can see that previously f is I scalar, and finally the result that we are getting as gradient of f is becoming a vector because it has I and j component. This df dx and df dy is the partial derivative f sub x, f sub y. So we know how to do the partial derivatives. So this is the gradient of f if f is a function of 2 variables. So similarly, if we have a function of 3 variables, then gradient of f will be del f. So del is a vector just like this one in 3 dimension. Del will be ddx I ddy j plus ddz k times f. So now f will be distributed with all these terms. So that is df dx I plus df dy j plus df dz k. So we understand that df dx is f sub x, df dy f sub y, df dz f sub z. So that means these are partial derivatives I, j, and k. So this is the gradient for function of three input variables, and this is the gradient for function of two input variables. So let's have a look on one example how to find gradient. So let's say we are going to find the gradient vector field of a function f of x comma y equals x squared y negative y cubed. So we can understand that this is a scalar function. So this scalar function has another name that is called potential function. So let's try to find the gradient. So gradient of f, that is del f. So it will be ddx I ddy j. So since it is function of two variable, this is the vector for del, and now it is f. So if we multiply ddx with f, so df dx I plus df dy j. So now we have to find the partial derivative, this one and this one. So let's do the partial derivative. Here f equals x squared y negative y cubed. So df dx will be ddx of f. So whenever we are differentiating in terms of x, then remember y will be constant, because this is the action for partial derivative. So ddx of x squared y negative y cubed. So let us separate the terms. ddx of x squared y negative ddx of y cubed. So since y is constant, y can be pulled out. Y ddx of x squared negative ddx of constant y cubed. So differentiation of constant is 0. Here we are getting y, differentiation of x squared is 2x. So finally we can write the result is 2xy. So this is df dx. Similarly, we have to find df dy. So f equals x squared y negative y cubed. Let's find df dy. That means we are going to differentiate in terms of y. So ddy of x squared y negative y cubed. Since we are doing the partial derivatives in terms of y, so this time x will be constant. So ddy of x squared y negative ddy of y cubed. So x squared is constant. We are pulling out x squared before. So dy of y negative. Differentiation of y cubed with respect to y. So it will be 3y squared, because we know that ddx of x power n is nx power n minus 1. So x and x are similar. Similarly, y and y are same. So y cubed, its derivative with respect to y will be 3y squared. So x squared, derivative of y in terms of y is 1. So no need to write 1. We have x squared negative 3y squared. This is df dy. So we can input the result here. So df dx is 2xy I plus df dy is x squared minus 3y squared j. So this is the gradient vector field of F. So we can see that previously we have a potential function that is a scalar, and by doing the gradient we have found the vector field. So sometimes we can also find the gradient at any point. Let's say we need to find the gradient of this vector field at one point. That means the value of x is 1, y is also 1. So this is the gradient. So gradient is also a function. So we can write this one as gradient of f of x comma y. So this is equal to 2xy I plus x squared minus 3y squared j. So we are going to input 1 1, x equals 1, y equals 1. So let's input 1 and 1. So gradient of f at 1 1. So 2 times 1, y value is 1. We have I plus 1 squared negative 3 times 1 squared j. So we are getting 2 times 1 times 1, 2 I plus 1 negative 3 j. So 2I negative 2j. So this is the gradient of f at 1 comma 1 point. So this is how we can also find gradient at any point. This point can be 1 2, then x equal to 1, y equal to 2. So we can find the gradient. Now let's talk about the directional derivatives. So directional derivative is based on gradient. So we have learned that gradient converts a scalar function to a vector. By directional derivative, that vector can be converted to a scalar. So the example of directional derivative in real life will be like this. Previously we have seen that, let's say this is the map of our country. So if we want to know the change of temperature from the northern part to the southern part, so the rate of change of temperature is changing with respect to the distance, so along this direction. So there is a specific vector here. So we know how to find unit vector along any vector. So this is the example of directional derivative. So directional derivative is denoted by du f. So du, that is directional derivative along unit vector. So we have to find unit vector first. So the formula of directional derivative of f is gradient of f at any point. Let's say the point is x comma y dot u vector. U is the unit vector of a given vector. So if it is a vector from this point to this point, then we have to find the unit vector first. Then only we can find the directional derivative of this part. Then we can understand the rate of change of temperature from this northern part to the southern part. So in short, we can write the directional derivative of f along u is gradient of f dot u. So here the dot product is coming. So f can be function of 2 variable or function of 3 variable. So if we have a function of 3 variable, then the directional derivative will be gradient of f at x y z dot u. So instead of this one, we can make it short, that is gradient of f dot u. So this is the convenient way of writing the directional derivative. So these are the formulas for finding the directional derivative in the direction of any vector. So if we have any vector, let's say we have a vector, this one. So for this vector, we have to find the unit vector so that the length of that unit vector is 1. Then we can find the directional derivative along this unit vector. So first of all, we may have a function. So let's say we have a function. This time, let's consider a function that is of 3 variables, x comma y comma z, which is equal to x times sine of yz. So our question is find the gradient grad f, then find the directional derivative of f at, let's say, any point 1 3 0 in the direction of any vector a equals I plus 2j minus k. So our target is to find the directional derivative, that is du f, which is equal to grad f dot u. So first we have to find the gradient of f, then we have to find the unit vector of this a vector, then we can take the dot product of these two. So let's find the gradient first. So the function is f equals x sine of yz. So gradient of f, that is, let's say, grad f equals gradient of f. So this is a scalar function. We are going to have a vector now. So this function is a function of 3 input variables. So that's why this del will be ddx I, ddy j, ddz k times f. So we have df dx, df dy, df dz with I, j, and k. So we can understand that now we have to find the partial derivatives df dx, df dy, df dz. So let's find. The function is f equals x sine yz. So df dx ddx of x sine yz. Whenever we are differentiating in terms of x, at that time y and z will be constant. Sine yz, since y and z are constant, yz is associated with sine, so sine yz can be pulled out because this whole part is a constant. We have ddx of x, so differentiation of x in terms of x is 1. We have just sine yz, so this is df dx. That means this part is sine yz. Similarly, we can find df dy. So f equals x sine yz. So df dy equals ddy of x sine yz. This time we are doing the partial derivative with respect to y. So remember, x and z are constants. So x can be pulled out, but y and z are associated, so that's why we can't bring z before. So here we need to be very careful. We have dy of sine yz. So x, now we can apply chain rule. Let's say this is y. Differentiation of sine y is cosine y. So the term that we have considered, that should be again in differential form. So this is the chain rule. We have x cosine yz. Now differentiation of yz, z is constant, so z can be pulled out. Differentiation of y, so differentiation of y is 1. So we have x z cosine yz. This is df dy. So here we have xz cosine yz. This is df dy. Similarly, we can find df dz. So f equals x sine yz. Now let's find df dz. That is d dz of x sine yz. That is d dz of this function. Since we are doing the derivative in terms of z, partial derivative, so x and y are constants, so x can be pulled out, but y can't be pulled out because y and z are together with sine, dz of sine yz. So we have x. Now let's consider this is z. So differentiation of sine z is cosine z. So the term that we have considered, we have to differentiate that term again. So we have x cosine yz, ddz of yz. Y is constant, y can be pulled out, and differentiation of z in terms of z is 1. So we have xy cosine yz. This is df dz. So df dz is x, y, cosine yz. So now we can input the I, j, and k. So plus this is the gradient of f. So we need to find the gradient of f at 130 point. So this gradient is a function of three variables x, y, z. So we have sine yz I plus xz cosine yz j plus xy cosine yz k. So now we want to find the gradient at the point 1 comma 3 comma 0. So x equals 1, y equals 3, z equals 0. Sine yz, the value of y is 3 and z is 0, so we are getting sine 0. I xz, x is 1, z is 0, so multiplication will be 0. 0 times something, 0, plus xy, x is 1, y is 3, cosine y is 3, z is 0, so 0 times 3 is 0, k. So sine 0 is 0, plus 0, plus 3, cosine 0 is 1. So finally we have 3k. So this is gradient of f at 1 comma 3 comma 0. So our target is to find the directional derivative. So directional derivative is denoted by this symbol, which is equal to grad f dot u. U is the unit vector. So let us write the formula of directional derivative. So it is duf equals grad f dot u vector. So we have found that gradient of f is 3k dot this u. So we need to find this unit vector. So we have a vector given. We need to find the unit vector of this vector. So the unit vector u, which is denoted as u hat, or we can use arrow sign. So u equals a vector divided by the length of that vector. Length is denoted by this absolute value of the vector. So a vector is given as I plus 2j minus k. So I plus 2j minus k, and the length of this a vector. So we know that the length is 1 squared plus 2 squared minus 1 squared, because we know if a is a1i plus a2j plus a3k, then length will be a1 squared, a2 squared, a3 squared plus with square root. So this is the formula. Here we have 1i plus 2j minus 1k. So 1 squared plus 2 squared plus minus 1 squared. So we have 1 plus 4 plus 1 I plus 2j minus k. So finally we are getting root over 6 I plus 2j minus k. So we have found the unit vector along this vector. So we can write in another way. we can write 1 by square root of 6I plus 2 by square root of 6j minus 1 divided by square root of 6k. So this is the unit vector. That means 1 over square root of 6I plus 2 over square root of 6j minus 1 over square root of 6k. So now we have to do the dot product. So by dot product, we know that the multiplication of the first components plus multiplication of the second components multiplication of the third components. So the vector 3k can also be written as 0I plus 0j plus 3k. So it is 0I plus 0j plus 3k. So 0 times this one 0 plus 0 times this one 0, 3 times minus 1 over square root of 6. So we are getting minus 3 over square root of 6. So this is the directional derivative duf. So we can see that finally we have found a scalar quantity. That means we can understand that directional derivative is associated with gradient. So now let's talk about divergence. So divergence of a vector field f is denoted by div of f, that is del dot f. That means we are going to have the dot product. So we know that del is ddxi plus ddyj. If f is a vector field of two input variable, then we have this two-dimensional vector del dot f. Let's say it is equal to pi plus qj. That means f has the components as functions. So pi plus qj. So by dot product, we know that first term times the first term plus second term times the second term. So it will be ddx p plus ddy q. This I and j are cancelled. So this is the divergence of any vector field if it is a vector field of two input variables. Similarly, if we have a vector field of three input variables pi, qj plus rk, then divergence of f will be divergence del dot f. So this is equal to ddx I, ddy j, ddz k. This time we have to take del as this one because f is a vector field of three variables dot pi plus qj plus rk. So finally we have dp dx dq dy dr dz. This is divergence of f. So let's solve one problem. We have learned that if divergence of a field is equal to 0, then we can say that field or the fluid flow is incompressible. So let's say we are going to find the divergence of f, where f is a function of three variables x, y, and z, that is equal to xzi plus xyzj minus y squared k. So we have to find the divergence of this vector field f. Besides this, we can also think about in another way. We have to check whether this vector field f is incompressible or not. Divergence is equal to 0, then only it will be incompressible. Otherwise, it will be compressible. So let's find the divergence div of f, that is del dot f. Since it is function of three input variables, so it will be ddxi, ddyj, ddzk dot f has three components p, q, and r. Let's say this is plus. So we have xzi plus xyzj minus y squared k. So plus minus y squared k. So divergence is one kind of dot product. So it will be ddx of xz. Instead of writing xz here, it will be convenient if we write xz beside this one. So it will be convenient to write plus dy of the second component xyz plus dz of the third component minus y squared. So we can see that we have to do the partial derivatives. First, let's do this one. We are differentiating in terms of x, so z will be constant, so z can be pulled out, ddx of x, plus we are differentiating in terms of y, so x and z will be constant, so these two are pulled out, dy of y. We are differentiating in terms of z, but x and y will be constant, so here we have y squared, so y squared is constant. That means differentiation of constant is 0. So this is the divergence of f. Now we have z differentiation of x is 1 plus xz differentiation of y is 1. So we have found the divergence of f equals z plus xz. So we can see that this is a scalar because there is no I and j and k. So this is the divergence of f. So suppose we want to find the divergence at a point 1, 2, 3. Let's say we want to find the divergence at 1 to 3 point. So how can we find? This is very easy. Divergence of f is also a function of x, y, and z. So let's input the values of x, y, and z. X is 1, y is 2, and z is 3. So 1, 2, 3. So z is 3 plus x is 1, z is 3. So we have 3 plus 3, that is 6. That is divergence of f at 1 to 3 point is equal to 6. So we can draw a conclusion that we have to check whether f is incompressible or not. So here we can see that divergence of f is equal to 6 or z plus xz. So this is not equal to 0. If divergence equal to 0, then we can say the field f is incompressible. But since the divergence this time is not 0, so we can say that this vector field f is not incompressible. That means it is compressible. So this is how we can check whether a vector field is compressible or not. So this is what divergence is. Now let's focus on curl. So curl of f, that is equal to the cross product of del and f. So since cross product deals with three-dimensional vectors, that's why f must have to be three-dimensional vector field. So let's say we have a vector field f equals pi qj plus rk. So the curl will be the determinant I, j, and k. First, we have to write the components of del. We know that del equals ddx I, ddy j, ddz k. So first, we have to write the components of del, and then the components of f, p, q, and r. So whenever we have studied the concept of cross product, then we have learned how to evaluate this determinant. Let's solve one problem directly. I need to mention here that if curl of any vector field is equal to 0, then we can say that that vector field is conservative. That means that vector field is irrotational. There will be no rotation around any point. If the curl is not equal to 0, then that is called rotational vector field or non-conservative vector field. So let's have a look on one example. Let's say we have a vector field f of x, y, z that is equal to y squared z cube I plus 2xy z cubed j plus 3xy squared z squared k. So we have to check whether the vector field f is conservative or not. For conservative, curl will be 0. So let's see what happens. So we have to find the curl of f, that is the cross product of del and f. So I, j and k. Del is ddx, ddy, ddz, and now we have to keep the components of f. So this is p, q, and r. So y squared z cubed, 2xy z cubed, 3xy squared z squared. So we have to find this determinant. First of all, let's work with I. So whenever we are working with I, then this corresponding column and row will be cancelled. We have this one. So the cross product of these two, we have ddy of 3x y squared z squared negative ddz of 2x y z cubed. So the first part is done. Let's do for j. So there will be a minus. So whenever we are working with j, then this column and this row will not be considered. So we have to multiply ddx with 3x y squared z squared. So we have this one negative ddz of y squared z cubed, then plus k. So now we have to work for k. That means this column and this row will not be considered. We have ddx of 2x y z cubed negative dy of y squared z cubed. So this is the curl of f. So now we have to do the partial derivatives. So first of all, let's do the first one. We are differentiating in terms of y. So x and z will be constant. 3 is also constant. So we can pull out 3x z squared before. We have dy of y squared negative. Here we are differentiating in terms of z. So 2xy is constant. Negative j. Differentiation of this part in terms of x. So y and z will be constant. 3y squared z squared has been pulled out. We have just x. Negative. We are differentiating in terms of z. So y is constant. Therefore, y squared is constant. ddz z cubed plus k. We are differentiating in terms of x. So 2yz cubed is constant. Differentiation of x negative. We are differentiating in terms of y. So z cubed is constant. We have ddy of y squared. So I 3x z squared, differentiation of y squared is 2y, negative 2xy, differentiation of z cubed is 3z squared minus j. We have 3y squared z squared, differentiation of x is 1, y squared, derivative of z cubed will be 3z squared plus k, 2y z cubed, differentiation of x in terms of x is 1, z cubed minus times differentiation of y squared will be 2y. So we have I 3 times 2, that is 6xy z squared, negative 6xy z squared, negative j 3y squared z squared, 3y squared z squared plus k 2yz cubed, negative 2yz cubed. So we can see that these two parts are same. So 0 minus these two parts are also same, 0 plus these two parts are also same, so 0. So finally we have curl f is equal to 0. So that means the vector field that we have f equals this one is conservative. That means it is irrotational. So we can leave a comment that since curl f is 0 or curl f equal to 0, therefore f is a conservative or irrotational field. So this is how we can find the curl. We can also find the curl of any function at any point x comma y comma z, let's say 1 comma 2 comma 3, like that, whatever we have done in the previous problems. That means in this problem we have found the divergence of f at 1 comma 2 comma 3. So similarly we can find curl at any given point. So this is what we know as vector calculus. It has many applications in several fields like electricity, magnetism, gravity, fluid flow. So that's all from me. Have a good time.